Let's change that. I want to go back to the way it was. So we have our first test on Wednesday. And the topics are everything through kinematics along a line. So we're basically done with all that stuff. I'm going to do a couple of examples today of relative motion problems. But after that, we're going to go on to two-dimensional stuff, and none of that is going to be on the test, okay? So no vectors. Particle kinematics along a line, yeah. No vectors or 2D kinematics. And the exams, so you've taken one quiz. The quizzes are, we did not? Oh, we had to cancel it. Okay. Two of my classes took quizzes. Not okay, well, the quizzes, you haven't taken one yet, are all just short answer questions about stuff I say in class to make sure that you're going back and reading the notes and trying to understand what I'm talking about. The exams are different. The exams are just problem solving, and they're problems that are very similar to the homework questions, you know, at least in the approach that you have to take to solve them. And so to get ready for this, you want to just go through those problems, make sure you understand everything. The way that makes sense to me to describe how you know, like when you're ready for the test, is this. If you could, so one danger is just sort of like you go over a question enough and you kind of memorize what to do. But ask yourself, like on a question, could you explain to someone else how to do that question? Could you explain why here you do like, okay, now you do, this is a negative because we put the zero position here and whatever, you know? If you could explain how to do the questions and answer questions about why you made the different choices, then you're going to do great on the test. Okay. Mm-hmm. Right. You have to understand how that affects the answers that you're giving. Yes. Um, it most often it's about, oh well, for a 50-minute class, I'd say 3 or 4. And I'll try to make sure that it's not that you don't feel really rushed. I'll try to make it a pretty, you know, most people will be gone before the time is up, you know. Yes. Yeah, I'll give you all the equations through the whole semester. Any other questions? Let's do some examples of relative motion problems. Okay, so first, let's say that a person is walking on one of those moving walkways at the airport. I guess running, actually. So a person is running on a moving walkway. The person can run 5 meters per second. And the walkway moves at 3 meters per second. according to an airport camera, how fast is the person moving? Um, well, I think this is the idea here is, everybody can do this in their head. But what you want to do with the problems like this is make sure that you're uh, getting that subscript approach straight, because the problems are going to get more complicated. Um, and so these easy problems, you don't want to get in the habit of just doing this stuff in your head, because it's going to mess you up later if you don't get the sort of method down. So um, there are three things that we're talking about here. So let's say G is the ground, W is the walkway, and P is the person. And we want to use a relative motion expression that relates these three things. We have three different forms of the relative motion equation: the position one, the velocity, and the acceleration, which is the one we want here. Velocity, yep. So we'll say the velocity of the person relative to the ground. And I'm just putting this together in a way that it meets that requirement of the, remember that fraction multiplication idea? The subscript fractions have to work out like you're multiplying them. So the velocity of person relative to the ground is equal to the velocity of the person relative to the walkway plus the velocity of the walkway relative to the ground. And if you multiply P over W times W over T, those cancel, so you know that this works. Um, yeah, that's right. The camera is like attached to a wall or something. So that's the not moving. Um, Almost all the time in these kind of problems, one of your references is going to be the ground. It's going to be fixed to, you know. Oh yeah, this is. Okay, so we're trying to figure out in this case the velocity of the person relative to the ground. The velocity of the person relative to the walkway, what's that? Yep, that's 5. And the velocity of the walkway relative to the ground? Yep, 3. And so person relative to ground is 8 meters per second. Okay, so let's do a similar example. So now let's say we're dealing with the same walkway. And it's moving at 3 meters per second in positive direction. The last example didn't have any negative stuff going on. It was all going in the same way. But now the camera measures the motion of the person. So the camera measures the person's velocity at -1 meter per second. Okay, so that means the person's moving at 1 meter per second in the negative direction, the opposite direction. Okay. Um, what would be person's velocity according to a person who's just standing on the walkway? Okay, so we know that well, here are the things we're going to have. Same as last time, we're going to have the ground, and the camera's mounted to the ground. We have the walkway, which has the same velocity as this second passenger just standing there. And then P is the person. Okay, so again, we have to come up with an equation that relates these three things, and the one that works here again is velocity of the passenger relative to the ground is equal to the velocity of the passenger relative to the walkway plus the velocity of the walkway relative to the ground. Do we know the velocity of the person relative to the ground? Yep, that's -1. Do we know velocity of the person relative to the walkway? That's what we're trying to find. And then do we know velocity of the walkway relative to the ground? That's +3, yep. And so now just solve for this. It's just an algebraic variable. So the velocity of the person relative to the walkway is -4 meters per second. So this time the person's going opposite the direction of the walkway, which is not safe. So don't do that. 4 meters per second is the speed. Okay? I guess let's just do one more of these. So now let's say that an elevator accelerates up at 1 meter per second squared as the person inside the elevator drops an object. What's the apparent acceleration according to a camera mounted in the elevator? Okay, so the things that we're dealing with here are the object, the thing that's being dropped, the elevator, and that's the camera that we're talking about in this problem. And then the ground. And I can relate these three things according to, do we want position, velocity, or acceleration? Yep, so acceleration of the object relative to the ground is equal to the acceleration of the object relative to the elevator plus the acceleration of the elevator relative to the ground. Do we know the acceleration of the object relative to the ground? That's right. That's right. We always, if something's in free fall, then according to the ground, the acceleration is always down at 9.81. So choose our positive direction up. So this is negative 9.81. Do we know the acceleration of the object relative to the elevator? No, that's what we're trying to solve for. Do we know the acceleration of the elevator relative to the ground? Yep, that's positive 1. And now just solve for the variable. Acceleration of the object relative to the elevator is equal to negative 10.81 meters per second squared. Okay. One thing that this brings up that's important in free fall problems, and we didn't really talk about this when we were talking about free fall, but notice the acceleration of free fall is down at 9.81 only for certain coordinate systems, only for certain reference objects. So an object in free fall accelerates down at 9.81 meters per second squared only for inertial coordinate systems. And that means, in other words, coordinate systems aren't accelerating. So far, since we're only doing things in one dimension right now, there's no such thing as rotating coordinate systems, but we'll see that when we go to 2 dimensions, there's another requirement that the axes of the coordinate system can't be rotating, can't be changing orientation in time. So if you choose your 0 to be mounted to something that's accelerating, then that free fall requirement doesn't hold. And we'll see that this inertial coordinate system requirement is going to be a big thing when we get to forces and stuff too.
So the only time when it accelerates would be when it accelerates up when the ball's slowing down, right?
No, the coordinate system cannot be accelerating to have that. So like right now, we're not accelerating very much. You know, we are a little bit because the Earth is rotating, but it's rotating slowly. But so sitting here right now, we're not accelerating very much. And so if you drop something, you'd measure a downward acceleration of 9.81. But if you, yeah, well, if you dropped something at the same time that you dropped a video camera, and then you measured, that video camera is like a new coordinate system, okay? And what would, according to that camera, now you're watching the video, trying to use that video to determine the acceleration of this object you dropped. what would that camera see as the acceleration of this object? It wouldn't see anything. They'd be falling exactly the same, and it would just see that if you didn't see the walls or anything behind it, it would look like that thing was just hovering in space, you know. But that's because this video camera is an accelerating coordinate system. If you're going to use that, whenever you're using that acceleration, that free fall acceleration of 9.81 down, you need to have that camera, and it's only accelerating. And so it's fine for that coordinate system to be moving. It just can't be accelerating. So it could be moving with a constant velocity. So elevators don't accelerate the whole time they're moving. They, get up to speed and then stay at a constant speed until they get where they're going. So if you wait past the acceleration and now the camera is just moving with the elevator is just moving with a constant velocity, and you drop something, at that point the camera will say that it accelerates down at 9.81. But if you use that camera to measure it during the brief period where the elevator is accelerating, changing velocities, then it'll look like that doesn't work. Okay. Any other questions about that? Yeah, let's do one more. Okay, so let's say you have one of those swimming pool things with the moving water, so you don't need a big space. And let's say the water is moving this way, and someone's in the water swimming. Oh man, their shoulders are messed up. E.T. phone home. Okay, this is better. Okay, so the water's going this way, and the swimmer's swimming in the other direction. And let's say that the swimmer can swim 1.5 meters per second, 2 meters per second. And the water in this pool is moving at 1.5 meters per second the other direction. So if the swimmer starts 2 meters from the side, the end of the pool, how long does it take for the swimmer to reach the side? So when I say side, I'm talking about this. The swimmer starts back here somewhere and is going a little bit faster than the water. So the swimmer is sort of slowly inching towards this side. And at some time t, the swimmer reaches that side. That's what we're trying to calculate. Okay, so the things that, sort of the objects that matter in this problem are the ground, the water, and the swimmer. And we can relate these three things using the velocity of, yeah, let's go. So there's not only one way you can do these problems. I'll show you that in a second, but let's go velocity of the swimmer relative to the ground is equal to the velocity of the swimmer relative to the water plus the velocity of the water relative to the ground. And let's think about which of these things we know. Do we know the velocity of the swimmer relative to the ground? 2 meters per second is, so the swimmer is capable of swimming 2 meters per second in the water. So if the water's moving 1,000 miles an hour, the swimmer's going 1,002 meters per second, I guess. Okay, so this is the one, swimmer relative to the water is, yeah, let's call that 2 meters per second. I guess let's choose a positive this way. And the velocity of the water relative to the ground, what's that one? It's the magnitude is 1.5, but it's going in the opposite direction that the swimmer is going compared to the water. Does everyone see that? And so this is negative 1.5. And so the velocity of the swimmer relative to the ground is positive 0.5 meters per second. And now how are we going to calculate the time that it takes to get to the side? We can use the constant acceleration equations. We know that position is equal to the initial position plus the initial velocity times the time plus 1/2 a time squared. These velocities are all constant, so there's no acceleration. That goes away. And so now we can say that 2 is equal to the initial position, 0, plus 0.5 times t. And so t is equal to 4 seconds. Any questions about that? Okay, so I pretty much always, you can usually pretty much always set these problems up where there's an object and there's like an intermediate moving thing and then there's the ground. And so I always have set up the object relative to the ground on the one side and then everything else falls into place. But you can organize these three things in different ways. So let's say that we had started out as, so what if we started out as the velocity of the swimmer relative to the water is equal to the velocity of the swimmer relative to the ground plus the velocity of the ground relative to the water. Okay. Well, remember that this is a little kind of an awkward way to write it because you don't tend to think of the ground moving relative to the water, but you could imagine if you had a camera floating in the current of the water and it was taking a picture of the walls as they went by. I mean, that's a measurement you could take. You just have to remember that velocity, and this is true for position and acceleration too, the velocity of A relative to B is negative velocity of B relative to A. Okay, so what do we know in this equation? Do we know the velocity of the swimmer relative to the water? Yep, that's the 2 meters per second. Do we know the velocity of the swimmer relative to the ground? No, that's what we're trying to find. And do we know the velocity of the ground relative to the water? Well, water relative to ground is negative 1.5. So ground relative to water is positive 1.5. Because this is negative velocity of the water relative to the ground, which is given. And you get the same thing.
So pretty much go from the object over the ground in like regular.
That's what I do. That's what most people do. So as far as the way the way you do these calculations is kind of a way that you're communicating with people who are grading your stuff, and later it'll be like people who you're working on projects with. I suppose that's a little clearer to people, but this is mathematically perfectly fine. I'd never take points off for you know, using a more unusual form of it. All right, so that is the end of 1D kinematics of particles. So now we're going to 2D kinematics of particles. And before we can do that, so uh, the next topic is 2D kinematics of particles. And before we can do that, we have to talk about vectors. So I'm going to go into a little thing about vector math. In lab on Friday, we already sort of talked about how to think about a vector as a mathematical object. In class, we're mostly going to focus on numerical math of vectors, not about like interpreting what they mean, but the idea of vectors is that in one dimension, there are only two directions. So positive and negative are enough to specify the direction. In 2D, so in 1D, there are only two ways, you only have two choices where you can go. We don't know which way the line is going, but say the line is like this. You can either go this way or that way. So you call one of them positive, one of them negative, and then that specifies the direction. But in 2D, if you're at this point, you can go infinitely many directions. And so positive and negative aren't enough anymore to specify the direction. So directional objects that have direction attached to them. And remember, in 1D, that was position, displacement, velocity, and acceleration. Those are all directional quantities. So directional quantities represented by vectors. And we're always going to think of vectors as an arrow in space. They work as well in 3D as in 2D. We're not going to do 3D problems, but there's not really any qualitative difference between 2D and 3D. So we're going to think of a vector has an arrow in space, and it only has two quantities, two properties, sorry. It has a magnitude, that's the length of the arrow, and it has a direction. That's where the arrow points. One thing, so this is all a vector is. It's those two things, and they're represented nicely by an arrow. But notice one thing that they don't have, it doesn't have a location. There's nothing about a vector that says it has to be over here or it has to be over here. So a vector over here with the length of my arm pointing that direction is just the same as this vector over here. Location doesn't come into it. And so what that means is for convenience, you can move vectors around and it doesn't change anything. We're always going to think of vectors as having their tail at the origin of the coordinate system because it makes it easier to do the math with them. And that's fine because we can put them anywhere we want. It doesn't change anything. So we'll always think of vectors with their tail at the origin of the coordinate system. Origin of the coordinate system. Okay, so vector examples. Okay, so this is what you've seen in lab, you know. That's a vector that conveniently for us lives in the two-dimensional space of the page, okay? But vectors don't always have to live in the space of the page, and so something you'll see sometimes is a vector coming directly out of the page. It's represented as a circle with a dot in the middle. Okay, that's out of the page. And that's just supposed to be a sort of a schematic picture of what it would look like if an arrow was coming toward you. You see the point there in the middle. Okay. And a vector that's going directly into the page, you draw an X in it, which are supposed to be like the feathers of the arrow going away from you. And the two most important calculations we're going to do are the ones that we talked about in lab. So the first one is adding two vectors. Normally, when you're doing problems, you're not going to add vectors this way, the way we did in lab. You're going to come up with vector components and then numerically add the components. But adding two vectors, think of, using the two vectors to create a path from the starting point to the endpoint. Then the resultant vector is just the shortcut from that same starting point to that same ending point. Resultant is the sum of those two vectors. So for example, if you're adding this and this, we'll pick a starting point, and it's arbitrary again because vectors don't have locations. And start out. Okay, we'll start out here. Okay, so we're at the starting point. We take either one of these two things and put it at the starting point, and now we're at a new spot where the head is. And then we'll take this. Come on. You son of a... Now I just got to draw it like a sucker. Okay, so basically, whatever, that looks pretty good. Okay, so we start out with one of them, get to a new place, then take the second one, get to the new place. This is our end point, and the resultant vector then goes from that starting point to that ending point. That's the resultant vector. And the order you take doesn't matter. Another way of saying that is that vector addition is commutative. It's a commutative operation. So say that we started out with this vector, and then followed this vector. The resultant goes from the starting point to the ending point. And if I did it carefully, those two red resultant vectors would be exactly the same length and exactly the same direction. And the second operation we're going to use a lot is multiplying a vector by a scalar. Scalar means number. It's making a distinction between vectors and non-vectors. And we can break this up into, just like we did in lab, multiplying a vector by a positive number keeps the direction the same. And multiplies the length by that number. That's only positive, multiplying by positive numbers. So if you want to multiply by a negative number, you can think of it as two operations in a row, multiplying by a -1 and then multiplying by a positive number. So to multiply a vector -1 switches the head and tail. So for example, if you start with that vector and let's say you multiply it by -3, you get that red vector back. So like you can think first I multiplied this by -1 and made it switch directions but stay the same length. And then I put 3 of them head to tail like this, and that gave me the final answer. Anyone have any questions about that? Okay. Well, let's stop there and we'll talk about dealing with vectors using their components tomorrow.